Okay, here is our notes for the Topic 6 worksheet. Basically, I'm just covering the rest of the Chapter 4 stuff here in these notes. So we'll get right to it. Problem 1, determine if f is a rational function and state its domain. Okay, the definition of a rational function is where you have a function of the form polynomial over polynomial. So the function given in A would be a rational function since we have a polynomial in the numerator and a polynomial in the denominator. State the domain. Well, of course, I know I can't divide by 0 here, so I would just simply take the denominator and set it equal to 0. I've done that here on the side. X squared plus 3x minus 10 factors as x plus 5 times x minus 3. And so when you set these equal to 0, you're going to have x equal negative 5 and x equal 2. That is what we don't want for values of x. And so therefore the domain of f, the set of all x such that x is not equal to negative 5 and x is not equal to 2. Part B, we've got another function given. So this is not a rational function. It's a function in fractional form, but I don't have a polynomial in the numerator. Okay, remember a polynomial has to be where you're adding up a bunch of terms, but every single power of x has to be a whole number. The square root of x is the same as x to the 1/2, and 1/2 is not a whole number. We still want to state the domain here, so again, I don't want to divide by 0. X squared plus x, if you set that equal to 0 and solve, x would be in common to those two terms. You can factor that out, and you'll have x equals 0 or x equal negative 1. And again, that's what we don't want for values of x in the domain. Okay, problem 2. Identify the horizontal or vertical asymptotes on the graph. Also state the domain of f. So we have the graph of some function, and remember we use a dotted line to represent an asymptote. So it looks like, and take note of the scale here, I'm using an increment of 2 on both of the axes. So here's 2, 4, 6. It looks like x equal 5 is going to produce a vertical asymptote, and then x equal negative 5 would be another vertical asymptote. And the horizontal asymptote would be, here's 2, 4, y equal 4 would be the equation of that horizontal boundary. Now, remember that the idea of an asymptote is that the graph gets closer and closer to the boundary, but it won't get there. Okay, so that's something that we'd want to recognize here with this curve, where we're not actually going to get to these boundaries, but they are boundaries on the graph. The domain of the function would be all real numbers except for 5 and negative 5. We don't have a formula representing f of x, but if we did, the way to get a vertical asymptote in general is just by simply stating the domain of the function. Okay, so like in part A, knowing that x can't be negative 5 or 2 means that I could know right away that there's going to be two vertical asymptotes on this graph. They would be at x equal negative 5 and x equal 2. They're not asking me to state any vertical asymptotes, but that would be something that I could conclude from knowing the domain of the function. So getting the vertical asymptotes should be pretty much immediate just by knowing the domain of the function. Okay, problem 3, we want to find the vertical or horizontal asymptotes. In part A, we have the function f of x. Now, I'd want to know the domain of this function. Of course, I don't want to divide by 0. So if I set x squared minus 9 equal to 0, and then solve, add 9 to both sides, and then take the square root of both sides, I'll have x equal plus or minus 3. Okay, now that would be what I don't want in the domain. Because I would be throwing away 3 and negative 3, I would have corresponding vertical asymptotes at x equal 3 and x equal negative 3. You could write it in a condensed form. X equal plus minus 3 means the same thing. Now, to get the horizontal asymptote, you're comparing the degree of the top to the degree of the bottom. The degree, again, is the largest power of x that we see. Whenever the degree of the top is less than the degree of the bottom, y equals 0 is always a horizontal asymptote. So in this problem here, I've got a degree 1 polynomial divided by a degree 2 polynomial. The degree of the top is less than the degree of the bottom, so I just simply write y equals 0. There's really no work to show. I can just get the horizontal asymptote pretty much immediately there. Okay, part B, same deal. I want to find the equations of the asymptotes. And so to get the vertical asymptotes, I'd want to be aware of the domain of the function. Well, if I set the denominator equal to 0, just somewhere on the side, x squared plus 4x minus 21 equals 0. That's going to factor nicely for us as x plus 7 times x minus 3. If you then set the factors equal to 0, you'll have x equal negative 7 and x equal 3. Because you would be throwing away those two numbers in the domain, they would produce corresponding vertical asymptotes at x equal negative 7 and x equal 3. To get the horizontal asymptote, again, we would compare the degree of the top to the degree of the bottom. Now here, the degrees match. Both of these are degree 2 polynomials. Whenever the degree of the top is the same as the degree of the bottom, as is the case here, we need to divide and we're going to disregard the remainder. We're going to have a horizontal asymptote, but it's not going to be at y equals 0. It's going to be at y equals some other number that is found through this division process. So I've set up the division process. Now notice here that my only option for division is to use long division. I can't use synthetic division because I am not dividing by a binomial here. So the expression in the denominator is going to go outside the division bar. The expression in the numerator will go underneath it. To begin, I need to think of an expression such that when I multiply by x squared plus 4x minus 21, the leading term is 3x squared. 3 times x squared plus 4x minus 21 gives me 3x squared plus 12x minus 63, so that leading term matches. That's what I wanted. When I subtract these expressions, 3x squared minus 3x is minus 3x squared is 0. 0 minus 12x is negative 12x, and then negative 1 plus 63 is 62. I am done dividing, and so my leftover is always going to be a fraction that I'll be adding to the quotient. The fraction that we want here is negative 12x plus 62 over x squared plus 4x minus 21. Now, after you're done dividing, you've completely divided, you're going to disregard the leftover here, and then you're going to write as an equation y equals whatever information is to the left. So y equals 3 would be the equation of the horizontal asymptote. A fast way to get the equation of the horizontal asymptote whenever the degree of the top is the same as the degree of the bottom is you're going to compare the coefficients in front of those leading degrees. So like in this problem here, I've got a 3 in front of x squared up top, a 1 in front of x squared down under. 3 over 1 is 3, y equals 3, and you're done. Like in this problem, I could have went right to the answer and said y equals 3. Here would be the work, behind the scenes to show where that would come from, though. All right, problem 4 is another one. Find the vertical or oblique asymptotes for the function. An oblique asymptote is a slanted asymptote. And okay, well, we can get the vertical asymptote right away, right? We see that 2 is a problem because we know we can't divide by 0. Because you'd be throwing away 2 from the domain, x equal 2 would be a corresponding vertical asymptote on this graph. And whenever the degree of the top is 1 more compared to the degree of the bottom, you're going to have an oblique asymptote. So I could know right away in this problem that I've got an oblique asymptote since I've got a degree 2 polynomial divided by a degree 1 polynomial. To get the equation of that asymptote, I again want to use division and disregard the leftover. So I suppose I could have used synthetic division here. I chose to use long division instead. I wouldn't care if somebody were to use synthetic division, just as long as you're still getting the same result. So let's just use long division. X minus 2 is going to go outside the division bar. 2x squared minus 5x minus 2 is going to go underneath it. We need an expression such that when we multiply by x minus 2, the leading term is a 2x squared. If you use 2x times x minus 2 is 2x squared minus 4x. Those leading terms match. When you subtract these expressions, 2x squared minus 2x squared is 0. Negative 5x plus 4x is negative x. You can bring down the minus 2, and you can divide again. So now we're looking for an expression such that when we multiply by x minus 2, the leading term is a negative x. If we use minus 1, negative 1 times x plus 2 is negative x plus 2. And again, we're subtracting. Negative x plus x is 0. Those leading terms are gone. That's what we want. Negative 2 minus 2 is negative 4. Negative 4 would be my remainder. The complete leftover information is a fraction that gets added to the quotient. So negative 4 over x minus 2, that would be the leftover. Now the equation of this asymptote would be found by ignoring the leftover here and then writing as an equation y equals 2x minus 1 would be the information that is to the left. Okay, and we'll take a break right there.